Hello everyone, welcome to the ninth episode of the series. In this video, we'll talk about matrix inverses. Last time, we studied matrix multiplication and some of its properties. In particular, uh, we saw that compared to real multiplication, matrix multiplication is not commutative. Uh, Non-zero matrices can multiply together and give a zero matrix, and cancellation of matrices doesn't usually work. And one thing that we did not talk about was matrix division, vaguely speaking, and that is what our goal for this episode is. So we're going to begin by recalling division in real numbers. Note that any division problem can be converted into a multiplication problem as long as we can find the inverse to the denominator. So we can write a fraction p over q as q to the minus 1 times p. This number q to the minus 1 is called the inverse to q, and it satisfies that q to the minus 1 times q is equal to 1, and so is q times q to the minus 1. Now we're going to generalize these ideas to matrices. First, we need to generalize the number 1 to matrices, and we've actually done that already. So the matrix I'm talking about is the n by n identity matrix. So recall that this is a matrix which has ones on the diagonal and zeros everywhere else. And remember that there is no such thing as a non-square identity matrix. So when we multiply the identity matrix to any other matrix, it leaves the other matrix A unchanged. And for that reason, identity is the matrix analog of number 1. Now, the analog for multiplicative inverse is the idea of inverse matrices. So in particular, if A is an n by n matrix, the inverse of A is the n by n matrix B, where A times B is identity and B times A is identity. And we usually denote this B by A to the minus 1, and we call it A inverse. Okay, so let's look at an exercise. So we're given two matrices, and we want to verify that the first matrix is the inverse of the second matrix. In other words, we have to multiply these two matrices in either order and show that we get a 2 by 2 identity matrix. So let's first multiply 18 minus 7, 5 minus 2 on the left. And when we compute this matrix product, we end up getting 1001. Feel free to verify this. And when we multiply the matrices in the reverse order, we again get 1001. Feel free to verify the arithmetic error. And because both AB and BA end up being a 2 by 2 identity matrix, we conclude that 18 minus 7, 5 minus 2 is the matrix inverse of 2 minus 7, 5 minus 18. Okay, so it's important to note that not every matrix has an inverse. For example, the matrix A that we see on the screen does not have an inverse. And to show that, we're going to, on the contrary, assume that there is an inverse. And if there is an inverse, we'll just call it A inverse. And if there is such an inverse, like a matrix inverse for A, then it would satisfy A inverse A equal to a 2 by 2 identity matrix. And if we multiply, this equation by the matrix B on the right, then A inverse AB would just be identity times B, and that would just be B. However, this computation on the left, can be rearranged as A inverse times AB. In other words, we use associativity to multiply A and B first. But if we multiply A and B, we get a zero matrix, and then any matrix times a zero matrix is a zero matrix. So what we've shown is that A inverse AB is 0, but at the same time, also B, but we know that B is not equal to 0. But we just arrived at the conclusion that B is equal to 0, which is obviously impossible, and therefore we get a contradiction. And for that reason, our initial assumption that A had an inverse was wrong to begin with, and therefore we conclude that A has no inverse. Okay, we've been talking about inverses and we've been using the inverse quite a bit. And that's because the inverse of a matrix is unique whenever it exists. And that's why we can use an unambiguous notation like, a to the minus one or a inverse. So if A inverse exists, we say that the matrix A is invertible. And if A inverse does not exist, we say that A is non-invertible or not invertible. Also note that if A and B are square matrices, then left inverses and right inverses are the same. So if AB is the identity matrix, then BA is also the identity matrix for any two matrices A and B. And non-square matrix, not have an inverse. So we can also use inverses to rearrange matrix equations, as we see in this example. So assume that AB is equal to C and A is invertible, then we can multiply both sides by A inverse on the left, and we get A inverse times AB equal to A inverse C. But now by associativity, we can write this thing as A inverse times A times B, and the product of the first two matrices becomes identity. So we end up getting B equal to A inverse C. And do remember that the order matters. And when I say order, I mean the order of multiplication. So whatever we do, we need to do the same thing on both sides of the equation. So if we're multiplying a matrix on both sides of this equality, we have to multiply them on the same side of the existing matrices. So here I'm multiplying A inverse on the left of AB, and I cannot multiply A inverse on the right of C. I would have to multiply A inverse on the left of C as well, like I did in the previous example. And like we have, two different notions of division. There's A inverse C, and there's C A inverse. And because the matrix multiplication is non-commutative, in general they are not going to be the same. But essentially both are C divided by A, vaguely speaking. So we never write like C over A. Like we always write either A inverse C or C A inverse to denote exactly what we mean. Okay, so let's look at another exercise. So let's say B is an invertible matrix, and we're given the identity BAB inverse equal to C. So we have to rearrange this equation to write a formula for A. So what we're going to do is we want to move this B and B inverse to the other side, and that's how we'll isolate A from the rest of the variables. So the first thing we're going to do is we're going to multiply both sides of the equation by B on the right. So when we do that, this B inverse B becomes identity, and identity times BA is just BA. And then to remove this B from the left, we're going to multiply with B inverse on the left on both sides. And this B inverse B is now identity. So we end up getting A equal to B inverse CB. Okay, so let's go through some basic properties of inverses. So assume that A, B, and A1 through AN are invertible matrices. Then the inverse of identity will always be identity. The inverse of the inverse of a matrix is the original matrix again. And if we have the inverse of the power of a matrix, that's the same as the power of the inverses. So in other words, A times A times A whole inverse is the same as A inverse A inverse A inverse. The inverse of the transpose of A is the transpose of the inverse of A. And if we have the inverse of a product of two matrices, the order of the matrices reverses as we essentially quote unquote distribute this inverse. So the inverse of AB would be B inverse A inverse. And we can obviously generalize to the product of n matrices. So if I have a product of n matrices even through AN, and if I take the inverse of that product, it's going to be AN inverse, AN minus 1 inverse, and we keep going back and up to A2 inverse, an A1 inverse. Okay, so if A is invertible, then for any integer like n, if n is positive, we just mean that it's a product of n copies of A. If n is 0, we just mean that it's the identity matrix. And if n is negative, then by A to the n, we mean that we take the inverse of A, and we take uh, minus n copies of that A inverse. So for any integers m and n, A to the m times A to the n is always A to the mn. Okay, so we can solve systems of linear equations using inverses. So assume that we have a system of linear equations in the matrix form. So A times x equal to b, where x is the vector of variables, b is the vector of constants, and A is the matrix of coefficients. If A is invertible, in other words, if we can find an inverse of A, then the system has a unique solution, and the solution is given by A inverse times the vector B. The idea is as follows. So we can write this vector x as identity times x, because identity times any vector is the same vector. And then we can rewrite this identity as A inverse times A, but we know what AX is. AX is B, so we end up getting that this vector x is A inverse times B. And if A is non-invertible, then we can't say much, because there might be a solution and there might not be, but we don't have this one-step remedy for all possible problems. Okay, so well, let's look at an exercise. We're given this system of linear equations, 2x minus 7y equal to 3 and 5x minus 18y equal to 8. And we want to use inverses to solve this system. So the first step is, of course, to turn the system into the matrix equation. So I'm going to use vector v instead of vector x, because my variables already has an x and I want to avoid confusion. So we convert this into a matrix 2 minus 7, 5 minus 18 times a vector xy equal to the vector of constants 3, 8. Now, from exercise 1, we know that A inverse is 18 minus 7, 5 minus 2. And we can solve for xy by computing A inverse B, where we know what B is. So we compute A inverse times B, and we end up getting it's minus 2 minus 1. And as a result, x equal to minus 2 and y equal to minus 1 is the unique solution to the system. And with this, I would like to end this episode. I will see you guys soon. Until then, happy learning.